All right, good morning, everyone. So if you're going to say anything in the chat, make sure that all panelists and attendees is checked off on your two instead of just all panelists. And was today we're going to be covering data visualization. So it'll be a bit of a refresher from the last module from the DataCamp tutorials. So if you have any specific questions about data visualization, please let me know. You can also use the Q&A. If you don't want to ask in the chat itself, but I'll try to keep my eyes on the chat so that I can see if you have any other questions. And I know last time there were some questions about what's going to be coming up. So this was the schedule that we set up. So we already did setting up Python locally, which was the first webinar. Then we did Python data structures and control flows. Then Mona went over writing Python functions and using comprehensions. We followed that up by exploratory data analysis with pandas and a little intro into the time series. Then last week was understanding pandas data structures, grouping, pivoting, reshaping. So a lot of the working with data part. And this week is data visualization. And next week will be tidy data and cleaning data. So there's some conventions around what tidy data means. And lastly, we'll go over thinking probabilistically and exploring distributions and probably something along the lines of inference. So those are the next 2 weeks, tidying data and thinking probabilistically. So that's the schedule that we have set for you. And when is the last exam? I don't know what the schedule is, but let me get back to you on that. Let me see the CourseWorks website. I don't know if there is really a final exam, but the final assignment is going to be due or be released on week 8, which is starting October 29th. Yeah, so program support. So no last exam per se. And really the passing criteria for this course is 6 out of the 8 courses on DataCamp and a 75% of the final assignment on Vicario, which is going to be due on or it'll be released on October 29th. The last due date, let's see. I don't know when it's going to be the last due date. Oh, 1 week from release. So try to get it done within 1 week and let us know if like you have any like other circumstances, and hopefully we can work through that, but try to get it done within the week after that it's released. So that would be, what would that be? So it'll be Tuesday, November 5th. I'm not quite sure. I can double check with Mona since she taught this course last module. So I don't know how long it's going to take. Let's see. But yeah, I can double check with Mona how long it's going to take. Okay. Any other last questions that we can help you with? And it seems like program support is here so that they can help us with some of the logistics stuff. All right. So, as most of you have learned, the two main ways of doing data visualization in Python is through the matplotlib library and the Seaborn library, which is a little bit newer. So some things that will help you is, let's see. First, let's import pandas as PD. So that's the benefit of using Seaborn, is that it readily accepts pandas series and pandas data frames. And then we'll also load matplotlib, pyplot as PLT, and then we'll just also load in Seaborn as SMS. So you can load those. Right. And some things that you can do is you can put percent matplotlib inline, and that's going to make sure that it'll suppress the text outputs that otherwise appears in the matplotlib graphs in Jupyter notebooks. So this will suppress those messages. Another thing that we're going to do is add semicolons at the end of the lines. So this will also suppress further text outputs. So we can do one that has it and doesn't have it. So those are things to keep in mind while you're using this in Jupyter Notebook. So maybe you were just playing around with it in the DataCamp REPL, but when we're working with Jupyter, you can do these things. Great. All right, and another thing we can do to set up our notebook is something called plot.rc params. And we could set a parameter for our figure.fig size. And this is going to be the height and the width. So maybe we want 15 by 8. And this is totally up to you. Maybe we could make this smaller. So maybe you want it a square too. So maybe you could do 8 by 8 or something like that. Play around with this, and that's going to change. I spelled something wrong. There you go. So play around with these figure sizes if you want to see different types of output sizes. All right. So the Seedborn library has a data set called Anscombe. So in my last webinar 2 weeks ago, we talked about the Anscombe's quartet, which is a classic data visualization that I would say makes a strong case for why visualizing data is important, because we looked at the different data sets. In terms of statistics, they look very similar from the mean, like the correlation or squared values and everything like that, right? But when we actually look at it in our plot, they look quite different. So to load it, I'm going to call a data or a variable called Anscombe. And let's load it from our data set. And the data set's name is also called Anscombe. And let's print Anscombe just to see what it looks like. So it's a 3-column data set. It has one is a data set. It's a discrete or categorical variable. We also have X, which is numeric, and Y, which is numeric, and it has a decimal floating point type of data. So we're going to have 4 different data sets. So we have our first one, second one, our third one, and our fourth one. So all of those are different data sets within the Anscombe's quartet. So I'm just going to subset the first Anscombe's data set into something called DF1. So let's say where data set equals and then capital I. And let's plot that. So I'm going to take df x and df1. So we're going to just create a scatter plot or bivariate. It's not a scatter plot yet, but it'll be a bivariate plot. So 2 variables. Oh, missed one. Okay. So this is what my output looks like. My window's a little bit small right now. Maybe I can enlarge that. Okay. Let's see. All right, I'll just make my visualization smaller. So where I set up my figure size, let's see if making it smaller will help. So I made it smaller so you can see that the figure size now outputs to something a little bit smaller. There we go. And you'll see that plot.plot is really just the most generic of just saying like plot something with matplotlib. So it doesn't know any better. And you can see that it outputs out a line chart. Now I'm going to put a semicolon behind it, and you can see that we have some text that's being outputted. If I run that again, the semicolon will actually suppress our messages. And so it's actually going to look a little bit nicer for you. So that's the reason why that we use semicolons after our plotting. one way to be more explicit about how we want our plot to draw our points is we're going to type in the X and the Y's for more data. And now we can put in a new argument called marker equals O. So now we can see that we have our markers being drawn. And here's a very helpful diagram that I've seen. So this is the anatomy of a figure. So if you have any questions about what the, I guess the verbiage behind these matplotlib terminologies. So the figure itself, you can see it's out here. So it's the whole charting area. The axes with an E is the area of the plot, which is the X and Y, which is made up of the one of the axis, it's with an I, is there's the X axis and the Y axis. We have the title, we have major ticks, minor ticks, which is the subticks, major tick labels. So we have minor tick labels here as well. We have line plots, marker plots. We have a grid within our axes. We have a legend, and then splines. So these are all different parts of the anatomy of a figure. So when we talk about axes, it could be with an E or an I, both referring to slightly different things. And so when we start thinking about adding in subplots, you have to start thinking about creating a figure, adding in axes, so on and so forth. All right. So now we're going to break out the rest of our data set into DF2. So it's part of Anscombe data set equals 2, DF3 equals Anscombe data set equals 3, DF4 equals Anscombe data set equals Roman numerals 4. All right, so now we've separated out each of our Anscombe's data set into 4 different parts. And I'm going to create our figure. So within plot or matplotlib, there's dot figure. So we're just going to create an empty figure called fig. All right. So within our fig that we created, this empty fig, we're going to create axes with an E. All right, so that's our subplots, the X and Y space. And I'm going to fig add subplot. Oh, I didn't run this. All right. Subplot, and within our subplot arguments, the first number is going to be the number of rows. So we're going to say 2. And then the second one is going to be number of columns. So this is going to be similar with like subsetting, right? So the first one is always rows and then it's columns. And then the next number is going to be the location of the plot. So we want it in the first location. Now we're going to add in our second one with the same fig add subplot. And it's still going to be a 2 by 2. And then the position is going to be the second one. And our third one is going to be in location 3. And our last one is going to be in location 4. So we've created all of our axes. So this is where our subplots are going to go. So we dictated the size or the shape, which is a 2 by 2 grid. And we have our positions 1, 2, 3, 4 for our different types of axes. And missed 4 here. Let me see if I can. All right. Did not like me writing over that, but we got that step since we already set that fig. Okay. So now we're going to actually go back and plot in our axis 1, which is our subplot that we created. So now it's going to be our x df2 df1, sorry. And marker type O. We'll do this for axis 2 plot df2 df2 y marker O. The same for axis 3. And finally for axis 4. We can also add in our title for our figure. So within figure, so we'll go back up to our fig object. We're gonna type in our title with our SUP title, Anscombe's quartet. And we'll also do a tight layout, so everything will be as compact as possible. So tight layout. So run that. So it's saying that the text is 0.5 location, and it's going to be called Anscombe's quartet. We created figure.tight, and now let's see what this looks like. So we can just call figure, and you'll see that it's a little bit tight, but we have our Anscombe's quartet. We have our data frame 1, 2, 3, 4, all plotted together. So similar to how you may have seen the visualizations of the Anscombe's quartet. We can see that this one is an actual linear relationship. This is actually not a linear relationship since it's curved. This one has an outlier, and this one is by no means has any relationship. So X itself isn't changing with Y, except that there's this like maybe like a misclassified data or something like that. So now you can see that just by looking at this data, it's really hard to understand what these points are doing, right? I don't think it's going to be very hard for humans to understand any of this relationship between X, Y until we can actually visualize this. So when we actually visualize that relationship between X and Y between our data sets, it's actually going to be pretty significant. So I think this is always a good example to show you why data visualization is very powerful. And I hope you all agree as well. All right, so going into our univariate plots. So I just kind of showed you how to lay out basically a basic overview of the layout of Matplotlib. So now let's dive into a little bit more into like the statistical graphing. So there's plot.hist, and we can just take our Anscombe dataset, and it's only a univariate plot, so you only need to put in one variable, which could be our X. It could also be our Y. So we could look at the distribution between our X and Ys. So we know that Y has a slightly right skew. So most of our data is going to be on the left-hand side, and it's going to be a sharp decline to the higher numbers. And this is a good way of looking at the distributions and how maybe even like the range of your data for one variable at a time. And when we do Seaborn, we'll look at a couple of other ones, like the Valen plot that will also give you a univariate, but also it could be bivariate if you look at it through a factor. And then we've been using the default in terms of bivariate. We want to look at two variables. And so we've been just doing plot, but Matplotlib does have a separate function called scatter for scatter plots. So we can do df1 of our X and df1 of our Y. And this time we don't have to specify any markers and have any defaults. It'll automatically just create a scatter plot for us. And we also have the box plot. So in our exploratory data analysis webinar, I talked about a statistician named Tukey who created the box plot in the 70s. And this was very revolutionary at the time because you can show a lot of great information about statistics in one plot. So let's see what that looks like. So what we can do is show, what you want to do is pass in a list. So we're going to create a list with our square brackets. So df1 of our just Y variable, and we can also add in the df2 of our Y variable. And then the next item on our list is going to be df3 of our Y variable. And lastly, df4 of our Y variable. I'm going to add in, after the two last square brackets, a new argument. I'm also going to label it. So labels equals another list, since we were passing in a list before, df1, df2, df3, and lastly df4. And I'm going to put a semicolon on it. And if we run that, now you'll see that we have a very nice box plot with our labels df1 through df4. And this is the distribution shown through a box plot of the distribution of our Y variables for each data set. So again, we have the median value, which is part of our central numbers. We have in the box, which is 50% of the middle 50 percentile. So anything within this box, the middle 50% or middle half of your data set is going to be within this bounds. And then we have the lower and the upper quadrant, which will fit most of the rest. And then we have some outliers that will be plotted out as year points. So lots of information shown in one graphic. But there's a new, more modern way of showing what a box plot looks like, and we'll be exploring that with the violin plot later. Okay, so those are all pretty much classic statistical graphs through using Matplotlib, which is the core, I would say, plotting or data visualization library in Python. But you can see that it's not really the nicest looking graphics. And that's where Seaborn comes in. So Seaborn does allow users to create much more aesthetically pleasing plots and more complex plots with fewer lines of code. So this is really, how innovation happens, right? People create something because there's a need for it. And after many people using it, they realize that this thing could be improved. And so Seaborn is this improvement upon the core Matplotlib functionalities. And we're going to use SMS now because that's what we imported as Seaborn. So to do so we're going to go back to the univariate plotting. And to do histograms, there's no hist function really. So it's now called distplot. So they kind of categorized up the distribution plots into one function called distplot. So if I do the default Anscombe again and do X, the default distplot will show the histogram of the distribution. So these are the counts with the KDE or the kernel density estimation function plot as well. So two different ways of displaying what distribution looks like. One is through a kernel density, and the other one is through the counts, which is the normal histogram that you've been seeing. So if we want to just look at the histogram, what I can do is use the same argument or same function, and I'm going to change the argument in it called KDE, which stands for kernel density estimation equals false. And now what I've done is I've turned off this kernel density estimation, and you can see the units have also slightly changed. So this is now in counts, where it's counting the number that falls within this bin. So again, to reiterate what a histogram is doing is it's binning up our data through our range into certain buckets. So our buckets right now are including two values. So 4 and 5 are going to be in this bin, how we're visualizing it. Next bin is also 6 and 7, then 8, 9, 10, 11, 12, 13, 14, and so on and so forth. When we look at this, this is actually the percentage of the data being falling within our range. So you'll see that the units are also slightly different in our two different visualizations. If we only want our kernel density, what I can do is turn off our hist instead. So hist equals false. Oops, okay. And all right. So if I do our same thing, SMS distplot Anscombe X variable with our hist equals false, now we'll just see our kernel density estimation. Does everyone know what a kernel density is doing? So a kernel density is really taking some kind of kernel, and oftentimes it could be a normal distribution. It could be any type of, the kernel could be set for anything. So here is the kernel statistic. So you can read about the different types of kernels, but here are some of them. So within the kernel function, it could be uniform, right? So you give all the same weights, or it could slightly decay at certain points. So what we're trying to do is basically create a normal distribution or whatever kernel you're using at the center of each data point, and it's kind of summed up and smoothed out across the range. And so if you use like a Gaussian, it's going to be very smooth, right? And if you use anything in between, there's like the quartic, there's like the triangle, which is a little bit more, the angle is sharper. So there's different ways of utilizing these kernels. So you can look at all of these different types of kernels that you could use. And what we're basically doing is creating this distribution, whichever one you choose as a kernel, and smoothing out the data points from that. And that's why it's basically counting up all those points and smoothing it out within that kernel function that you're using. So that's how we get the smoothed out density of, based on the points that we have, we can estimate the density that we would expect from this distribution. So together, this is kind of what it looks like. So we smoothed out this distribution. And lastly, to help you kind of visualize maybe what that might look like, is this rug plot. So I'm going to keep hist equals, actually, let's just do rug equals true. So if I do the rug now, you can see that it's another way of showing you the distribution. So you can see where the actual points lined up. And now you'll see that this is how that kernel density was also formed based on their values. So there's nothing at 0, but it's just estimating that there will be, based on some of the smoothing parameters. The histogram really just shows you the counts, but sometimes there might be overlapping counts. So here it's going to show you that there's more higher values up here. So I think these are all pretty cool. And so you can see how the normal histogram, which was in part of the classical data visualization packages, has been extended into showing more and more data. So the code again is, if you want to show those dashes at the x-axis, rug equals true. And I'll share the IPython notebook that I'm working off of right now later, so you can go back and work on it yourself. To turn off the histogram and just show the density plot, is going to be hist equals false. And then to turn off the kernel density and just show the histogram is KDE equals false. So the default is to show both. So you just have to say which ones you want to turn off. And the only one you need to really turn on is the rug plot. So if you wanted to be more specific, you could do KDE equals true, hist equals true, and run that, and that's pretty much the same thing. So the only thing that's not default is the rug equals true. Usually it will be rug equals false. All right. So up until recently, there wasn't a scatter plot function. So what you could do is SNS, I think it's, let's see. If you do this, maybe I don't need that. SNS.version, you can see what version you're running. So I hadn't updated my Python packages in a while, so I was running 8 something. So I just downloaded it to see which version I was running. But now there is a scatter plot, but previously there really wasn't any. So this is why people were using something called regplot, which stands for regression plot. But now there is just a scatter plot function available. So I can show you both ways of doing it. But you can see that any of these packages are evolving all the time because people want different features added, and someone will go and make those features available. So things do change. So if there's something that you really want, you can either make it yourself, or you can write maybe like a ticket in GitHub, and someone might be able to make these features for you. So the old way of doing it was with this function called regplot, which stands for regression plot. So x equals x, y equals y, and data is our Anscombe. Actually, let's do df2. And oops, I forgot the semicolon. Let me rerun that. So now what you'll see is that the regression plot just prints out a regression, a scatter plot with a regression, which is maybe not the most exciting thing for you to happen. But you can see that it plotted out our x and y locations for our points, and it has added this simple linear regression line with the confidence interval. So you can kind of see now that if we were to plot out the residuals from our ordinary least squares, so you can see that in this area, all of our errors are going to be negative, and all of our errors are going to be positive in the middle, and then goes back down. And so you'll see that throughout our range, our errors are actually not distributed normally. And so you'll see that just by looking at this, that this linear regression is probably not the right model to be fitting to our data, because the errors are very dependent on the location of our model. If we want to remove our regression line, what I can do is take that same line of code. So SNS.regplot, and our data is x, y, df2, and fit reg equals false. And so now I didn't explicitly say call out our variables, but we have our x and y, and I removed our linear fit. So that was really the way of using scatter plots before. But now there is a way of doing it without showing it. So SNS scatter, and same I think I need to call this slightly different, sorry. It should work. Oh, because I don't think it's a pandas object that likes that. Let's see if this will take. Okay, there we go. So since it's an array, we can just feed it in like that. And so now we don't have to futz around with this fit reg equals false. So you can just immediately put in these two arrays. All right, and we'll get back to scatter plots in a second. But moving on, there's also joint plot, which is going to combine the last two things that we've been talking about, which is super exciting. So we have joint plot. So I'm going to say we're going to feed it in X and Y, and we can feed in df2. So now what we can see is that we have our scatter plot and we have our histogram or distribution of our X and our Y axis. So I'm going to actually go and make this a little bit smaller. So let's see, 4 and 4, just so that everything runs a little bit nicer in my, all right, so slightly smaller. All right, so now you can see that joint plot has shown our scatter plot, and now we can see the distribution along our Y and our X. So this would be really powerful if you have a lot of data points and you kind of want to see the distribution of your plots. So this is a little bit more complex than something that you could do in Matplotlib with just this really simple function called joint plot, right? So this is why people call this a high-level data visualization language. Okay. Along the lines of having too many data points, right now, we don't have too many. So we could show you, I'm going to just copy this part. And say we're going to be working with all of our Anscombe's data set, right? So Anscombe. So if we looked at that, there's some overlapping data points and some of it is very dense. And so this might not be really easily accessible for someone to see. And I know that everyone's probably going to be working with way more data points than just this small fraction that we've been working with, just as a toy example. So from the joint plot, we can actually visualize our data in different ways. So I'm going to do the same thing with our joint plot. Our X is going to be called X. Our Y is Y. Our data is going to be Anscombe. So we'll take the whole data set. And this time we're going to say kind equals hex. And I forgot the semicolon. So now what we're showing is we're hex binning our two-dimensional space, our X and Y. And what we're doing is we're creating a density within these hex bins of the number of points that fall within these hexagons. So we still have the distribution of our values, and we've kind of obscured by aggregating up the points so that you can see within these areas how we might view the density of our X and Y points. So from something that looks like this, we're now able to create kind of a density up to a hexagon using our hexagon bins to look at what the density looks like. So now we know in this dark blue area that probably has the largest number of points. And so another way of doing that is something called the KDE plot. So this time I'm going to do it slightly different. So you need to to call data and data2. So data, lowercase, is going to be Anscombe's X, and data2 is going to be Anscombe's Y. I'm going to close that out. And now this is going to show you the two-dimensional version of our kernel density estimation. So if you thought before about the one-dimensional space of just the axis, right? And we had the kernel, which was, in our case, the kernel statistics was basically a Gaussian or normal distribution. And we were counting up those points and smoothing it out over one dimension, right? Just along the x-axis. Now, if you think about the x and the y-axis and summing up and creating a normal distribution around a two-dimensional space, this is what the kernel density estimation is basically doing. So if you think about a topographic map, this is basically what it looks like, right? So you could have some features like elevation or temperature, something that might be continuous, and you're going to be creating a surface or an interpolation. That's the estimation of the values that we don't have captured as a smooth surface. So just another way of visualizing this density right here through the smooth kernel density estimation. Where here is kind of more coarse, and you can still see where the distributions are. And here we smooth out those values for you. And if we want to bring those all back together, we could do SNS joint plot x equals x, y equals y, data equals Anscombe's. And last time we did kind equals hex. We can also do KDE for kernel density estimation. And now we have this beautiful looking kernel density estimation map, which is our plot, which is our two-dimensional kernel density estimation. And here you can see the one-dimensional kernel density estimations. So if you were to basically sum these up across the space of the y and the x, this is the manifestation of that two-dimensional space where we were mapping out the one-dimensional spaces on the axis. All right. So that's getting a little bit more complex, but really it's just another way of showing your data. So if you have a lot of data points, this might be a good way of displaying that instead of putting like all the scatter plots, because at some point it's going to get really unintelligible for any viewer. And you know, with big data and big data visualization, that's a huge open research area about how to visualize all that data that we're now collecting. And so there are simple ways of doing that, and even these will eventually fail, right? Because there's just too much data. So let's start talking about box plots. So in Seaborn, we have our box plot function. Our X is going to be data set. So if we look back at our Anscombe's data set, so our data set is actually a categorical variable. So we can use this as our discrete values for our x-axis. So we can break it up by data sets. And then on our y-axis, we can choose any of these continuous or numeric data types. Kind of like how we did here, where we actually cut it up specifically for box plots. This will take it in a lot simpler. So data sets will be on our x-axis. Our y-axis we can just call y. And our data is going to be Anscombe's. And if I run that now, you can see that the x-axis is our categorical variable or continuous or discrete. So 1, 2, 3, 4. And our y variable is going to be our actual values for y. So very simple. We didn't have to do any of the data cutting, and it worked very nicely. So I was starting to talk about why the box plot might not be as relevant anymore. It's because what this does is it kind of obscures what the actual distribution looks like. So in our values here, we can kind of guess that this is the median, and within our middle 50%, there's a short chunk here, so there's probably going to be a lot of values and less values here. But how it's being drawn is that this box is making it look like the distribution is all equal throughout this box. Unless you're a very perceptive person, so shapes like this, where the median is very central in this box, that box shape is not going to be, this box shape is going to be pretty symmetrical. But if the median is slightly higher, that means that 50% of this the top 25 within the middle 50%, the top 25% is really all concentrated within the small band, where the other 25% is in this big box. So you can see how that might be slightly misleading if you don't know how to read this chart. So to get over this, and also if you think about these whiskers, the length of it is also showing you a little bit more about the distribution, underlying distribution, which might not be super clear for most people. So the file-lim plot really helps you see that and visualize that better, because it's actually going to plot out that kernel density estimation distribution straight onto this box plot instead. All right, so same arguments, different function called file-lim plot. So now if we run that, you can see that here is the distribution. So the actual kernel density estimation of the density of our distribution for each location. So you can see where we expected that most of our data is in the top part in our data set 2, and there's a long tail here. That's very true. So you can see that this is pretty illustrative, and it was very revolutionary back maybe 40, 50 years ago. But really, now that we have this kernel density estimation, and that calculation and computation is so much easier, we can easily calculate this, right? When this was created, this was done at a time when people were still doing manual graphics, and they were drawing this by hand. So if you think about the limitations that they face, it's very great. Where now we have all this computational power, so we can rely on the computer to make all these statistical graphics for us. So really the limitation is the computation that the machine can do, and not really what our hands can draw, which is quite a big revolution in terms of data visualization. And so far, we've really been talking about univariate and bivariate. Oh, so the last thing I want to touch on really quickly is, let's load up our iris data set so that I can show you. I'm just going to copy from my notes since we're running out of time. So we can use colors on top of our bivariate plot. So now we're adding a third dimension of data visualization. So now we have our X and Y and a class on top of the space. So if you want to include more data and more dimensions, you can do this a couple of different ways through faceting by making subplots of each group. You can also do it by adding in a color. So color is a new dimension that you can add. You can also use shapes. So here is one with shapes, I believe. So you can also add shapes as a third or fourth dimension. And you can also use size as an indicator. So you can see that by adding in different ways of drawing out your points, you can actually add way more dimensions than just this X and Y. You could add in the color or the shape, or even break it out into different subplots to show even more data and break it down. But that's a little bit about the data visualization and talking about how it might be helpful for your audience, and thinking about the evolution of how these data visualization techniques have evolved over time through looking at Matplotlib all the way into Seaborn. So I'll share with you the document that I've prepared for you. And most of this has been taken from a couple of websites that are also made clear on the bottom. Any last questions before we call it a day? All right, I guess that should be it. And just to reiterate what our program support is saying, the final assignment on Vocarium will be launched in the final week of week 8, which is launching on October 29th. The due date will be November 5th. Instructions will be emailed to you in the week launch email on October 29th. So really make sure you look out for that final week assignment. And if you can, please take the survey at the end. Again, it's really helpful for us to get feedback from those of you who are attending. And I will see you in 2 weeks. And in the meantime, message me if you have any questions, but hope you have a great rest of your day. All right, bye everyone.